Hello everyone. So welcome to the fourth week of the interaction session on the course on uh, basics and selected advanced concepts in robotics. So just an introduction. My name is Soumya and I am a PMRF fellow or a PhD student basically at IIT Gandhinagar. So I am your TA for this course. So um based on what you have learned until now, it was mainly kinematics of serial robots, right? You learned initially it was a basic introduction to robotics, science, and technology. You came to know what are the main elements of the robot and how do we model and analyze the robots, right? But in the second week, we moved ahead with rigorous mathematics for DH parameters. So we understood the reasons why do we even go for DH convention, and then we also saw what are the link transformation matrices, what are joints, what are links, etc. Right? Last week we dealt with kinematics of the robots. We saw direct kinematics of serial robots and saw that they were pretty easy. But for inverse kinematics, we can have more than one solution. So inverse kinematics was not that straightforward, right? We also saw elimination theory. We saw Sylvester's method to find the inverse kinematics. We saw how do we eliminate the variables, and then we find what should be the correct joint angles, or basically joint variables, right? We also saw why do we even go for optimization problem, and we try to minimize the thetas of the robot, the square of the thetas of the robots, right? We saw all of these things. So I hope you have gone through the lecture for week 4, and you might already be familiar that we are dealing with kinematics of parallel robots today. So there was a basic introduction, then you might have learned about loop closure and where and how do we break the loop, why do we even break the loop there. You might have seen that we started with 4-bar linkage mechanisms, right? And we called it to be parallel robots, and then we moved forward. Okay. So then there were many, there was a lot of content on mobility of parallel manipulators, and then you might have seen that direct kinematics here is not pretty straightforward, but inverse kinematics is straightforward, right? So you might have already seen all of these. In the next week, we'll see what are the applications of parallel robots. So we'll see sun tracking manipulator and Stewart Gore platform for four-stroke sensor, but that is something that we'll cover in the next class. And yeah, the applications will be covered in the next class, but I hope you are well versed with the concepts that have already been taught and you have watched the lectures. Okay. Just for a quick demo of what a parallel robot looks like, I would switch my screen to my window, and I want to show a video. So just hold on. This window capture I need to change to Microsoft Edge. Okay, and then I need to present my screen, entire screen. Okay, I hope you are able to see my screen. So here we have a video for parallel manipulator. So if you see this, so initially we had seen what are serial manipulators and what are parallel manipulators, right? So a serial manipulator is basically a connection of links, and then at the end we have an end effector. But here in this case, we basically look at a particular base, and any one of the links can be the end effector, uh, for which we want to have a certain position and configuration. So it can be defined corresponding to a particular link, but then there is no fixed end, and there is a fixed base, and then there is a mobile base. So if I play this video, you can see it. So you see the base is fixed, and then all the links linkages are there between both of them. So there is a revolute joint standing on the top of the base, which actually moves it in different direction, and all these links are controlling the mobile base of the robot. So this is an example of parallel manipulator. You might see it is not serial, it is parallel. Why parallel? Not because the links are in parallel, but then all those links actually connect to the mobile base and the fixed base. Right. If I show you another example, you can see this.
Welcome to my channel, Chair-Eye Design. Hope you like this video.
So they have a number of motors. And then they
Welcome
are
to my
also
channel,
trying to
Chair-Eye
control it.
Design. Hope you like.
Okay. I think these examples are, yeah, one of the videos. Basically, they are simulating as well as they are having the robot at the bottom, and and they are trying to control the motor. So you can see motor 1, motor 2, and motor 3 are present over here. Right. And then they are trying to, so these are also the motors. So basically, all of them are being used to manipulate the position and orientation of the mobile base in the which is at the topmost position. Might also see that a user is basically telling that where all I need to have the centroid of the mobile base, and accordingly the motors are being driven so that it reaches that particular position and orientation. A very good example of inverse kinematics. Okay. Okay, I hope we are done with this. So coming back to the call, I'll switch it to my screen back. Let me change my recording screen. Okay. Efficiency in what terms you are talking about? Like efficiency has to be if you're mechanical. That means in terms of power, do you want to know? Like it completely depends on the motor. Okay, it completely depends on the motor. What is the torque if you are able to achieve the torque? If you have the same motor, so the application is completely different. So definitely you are going to have more motors here. You are going to orient or position a base. So you have more number of links, you have more number of motors, you might also have prismatic joints, and when you have these number of things, so definitely the cost would be higher here. And in terms of efficiency can be defined if you compare the things. So the goal of serial manipulator is not same as that of parallel ones, right? So we cannot directly compare that which is more efficient. The applications are itself very different. For where you have a requirement of parallel manipulator, you cannot use a serial manipulator. So when we see the applications, we'll see that this cannot be done by a serial manipulator. So that way, but parallel manipulator is more stable because of the number of links that it has. So you see from all the sides it has a number of links, and then it provides a very good support, and you can increase the motor torque and all of that. So it really depends on the application. Okay. So let me, okay. So what we have seen, or what we are going to deal with today, is parallel manipulators, right? So what until now we just studied serial manipulators, right? What they had one open chain from base to the end effector, and today we study manipulators but with closed loops. They are called parallel manipulators. I'll come to all of that shortly. But before that. So what is a parallel manipulator? We'll have some questions also. Uh, let's say after some time, when once we discuss all the concepts. Okay, so a parallel manipulator is a mechanism where there exists one or more closed kinematic loop. Okay, and there is no natural first or last link, right? Because we might be interested in any of the links related to the mobile base or related to the ones that we have in the parallels of the manipulator. So yeah, we they do not have any natural first or last link, and the output link about which we are interested, for which we are interested, must be chosen. Okay, and total number of joints is more than the degree of freedom of the robot. So maybe the robot can only move in x, y, and z direction and roll, pitch, and yaw, but then it can do these, but the total number of joints it might have would be more in terms of prismatic and revolute joints. So we'll see that when that happens, and we'll see the concept of passive joints as well. That would be in a while. Okay, so how do we go about this? Let's define configuration variables. I'll change the color. This appears to be light. Okay. Configuration variables. Okay. So our configuration variables can be defined by Q, which is theta and phi. Okay, don't confuse this with roll, pitch, and yaw. So why I'm writing this, I'll tell you. Where theta is equal to theta 1, theta 2, theta 3 up until theta n. They can be actuated joint variables. Okay, जिसमें सच में मोटर लगा रखा है. But phi, which is phi 1, phi 2, and so on till phi m, would be passive joint variables. Okay, so what is my dimension of configuration space? It is n plus m, where n is also the degree of freedom of the robot. So how many degrees of freedom does it have? The number of actuations you have, but then the other joints are passive. Okay, so let's talk about the very famous planar 4-bar mechanism. Okay, so if I talk about this, so there is a base, then there is a joint over here from where you have a link 1. Let's call it to be L1. Then there is another link which is L2, and you have, so let this angle be theta 1, this angle be theta 2. Okay, and then we have another revolute joint here, and then we have link 3. So this is 4-bar mechanism, and for this we can define the angle. So it is theta 1 here. I should not write it here. It is phi 1. So it has 4 joints, and this, sorry, I'm sorry for what I said earlier. This is a passive joint. This is also a passive joint, and then you have it fixed over here. All right. Now, so what happens here? One thing is, this is called coupler. Okay, L2 is called coupler. So 1 degree of freedom mechanism with 4 joints. It is very well known. As I said, link 2 is called coupler. And is the typical output link, because its position and orientation is something that we want to control. Okay, so so let's call this length to be L0. So let's write it properly. L0 is ground link. Okay, L1 is input link. L2 is coupler, and L3 is output link. Okay, the joint angles, for joint angles, uh, theta 1 is angle of link 1. Okay, phi 2 is coupler angle, and phi 1 is output link angle. L0 is distance, L1, L2, L3, L4. Sorry, L0, L1, L2, L3 is something that you understand, right? It is basically the length. Theta 1 is the actuated joint angle, so this is actuated. But phi 1 and phi 2 are passive joint angles. These both are not actuated. Okay, but they are revolute joints, and then they can move. So just by actuating this joint, we want to, if let's say this is the output link, then we want to arrive at a particular position and orientation corresponding to this link. So there is something called loop closure concept. I hope you have gone to the lecture and you have understood this, but let's see what it is. Loop closure concept, what does it mean? I think there was a message. Missed it. In high speed, the flexibility of joints affects the movement. Yes, it does. Okay. So here, loop closure concept. So what do? We start at left point, go around, and return to the same point. Okay, so let's do it in this way. So we our L1 vector plus L2 vector, these two vectors L1 and L2, where they are reaching, should be equal to L0 vector plus L3 vector, right? This is just simple addition of vectors. So if I write in the terms of components, so what it would be, let's do for LHS. Okay, so XL for left. Okay, L1 cos theta 1 plus L2 cos theta 1 plus phi 1. This is very simple, similar to what we did for serial robots, right? YL is L1 sine theta 1 plus L2 sine theta 1 plus phi 2, right? For RHS, what it would be? XR is equal to L naught, because it is just this link L naught. L naught, and it does not have any component because we assume the axis to be along it. So L naught plus L3 cos phi 1, and YR is equal to L3 sine phi 1. Okay. So now we have to equate this, right? So, okay, L1, what we got for x? L1 cos theta, theta 1 plus L2 cos theta 1 plus phi 2 is equal to L0 plus L3 cos phi 1. So I basically equated the left and right side of the x equations. For y, it is L1 sine theta 1 plus L2 sine theta 1 plus phi 2 is equal to L3 sine phi 1. Right. After doing this, what do we do? How can we solve this? Can we have all the terms on the left hand side, all the terms constituting L0, L1 and L3 on the left side as the first term, and the second term consisting of all the sine terms, and on the right side can we have L2 square? So I'll write the equation directly, and it's called Friedstein equation. So okay, and what does it say? It says square and add. And what I have to square and add? So I'll just rearrange the terms and show you the addition here. L1 cos theta 1 minus L0. I have taken this term to the left hand side. Minus L3 cos phi 1. I have also taken this term to the left hand side. And only L2 will lie on the outside. Cos square plus L1 sine theta 1 minus L3 sine phi 1 cos square is equal to L2 square. It's just squaring and adding. Okay. After simplifying this, when you try to simplify, you will find it would be in terms of some p cos phi 1 plus q sine phi 1 plus r is equal to 0, where your p would be 2L0 L3 is just simplification. I'm not doing it right away, but you can do it. This can be your homework. Theta 1. Q is minus 2 L1 L3 sine theta 1, and your R is L0 square plus L1 square plus L3 square minus L2 square minus 2 L0 L1 cos theta 1. Okay. Once you get this, get the equation in this form. We already saw half angle substitution, right, the previous time. So you can write solve for phi 1. And how do we solve for it? Using tangent half angle substitution. And what do we do here? We write phi 1 is equal to 2 tan inverse minus q plus minus under root p square plus q square minus r square upon r minus p. Okay, and what is the physical meaning of this? If p square plus q square minus r square is less than 0, that means no real solution is there and mechanism cannot assemble. Okay. Okay. Let's talk about degree of freedom. This is very important. Okay. So we have already seen last time Grubler Kachback formula. Can anyone remind me what it was? Degree of freedom is equal to what? Come on, this is important. No one knows? Okay. So it is lambda into n minus j minus 1 plus sigma fi, where I goes from 1 to j. What these terms individually mean? N is number of links. Okay. J is number of joints. Fi is degree of freedom of ith joint, and lambda is 3 for planar and 6 for spatial. Right? So for our 4 bar example, let's see what it is. So in our 4 bar example, what is n? How many number of links do we have? How many links do we have? No one is responding. Come on, it is easy. How many links does it have? The 4 bar mechanism. I showed you right now. How many links does it have? You can type in the chat box. The answer is correct or wrong. It does not matter. I need to know if you are able to understand. Okay, I'll move forward since you guys are not replying. Okay. So number of links that we have are, I'm still asking if someone wants to answer. What are the number of links? What are the number of joints? And what is the degree of each joint? Degree of freedom of each joint? And then you might already know if it is planar or spatial. Okay, I won't uh, waste a lot of time on this. So here n is 4 because we have 4 links. Number of joints are 4, right? Because we have 4 joints, 1, 2, 3, and 4. Fi, so all of the joints are revolute joints. So 1 each. So if we'll do the summation, it would be 4. And lambda is 3 because it is a planar robot and it is not like spatial. Okay, so degree of freedom is lambda. So if we go with this formula, lambda is 3, n is 4, j is 4 minus 1 plus sigma fi from 1 to 4 would be 1 each, then it would be 4. So it's going to be 4 minus 3, which is 1. So it has 4 links. It is a 4 bar mechanism. But if you see, it has just 1 degree of freedom. All right. So a very important statement here is your J is greater than degree of freedom. What was J? J was 4, degree of freedom is 1. Okay, and it is very important in case of parallel manipulators. So what are number of passive joints? It is J minus degree of freedom, which is 4, sorry, 4 minus how many degrees of freedom do I have? 1. It is 3. So the number of passive joints are 3. By the way, just to clarify one thing, that the way I did vector addition here, this one, I hope all of you understand this, because what I did here basically is I took this, I'll change the color. I took this link 1, I took link 2, and then I got a vector here, right? Then after that what I did, I took another link from here and added with it, and then I got this position. So basically I am concerned about this position, right? And I'm trying to equate them here, that the x and y should be equal here. I'm doing that. But what you can also do, you can, instead of equate, so I broke my loop here at this point. Okay, I broke my loop here. I broke my loop here. What you can also do, you can break your loop here, 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 or anywhere else. If you are breaking your loop, let's say here, then what you are going to do, you are going to have, let's say the length of this part is a and this part is b. So a plus b has to be a constant, which is L3. That is it. But you can break the loop anywhere. And you have to write the kinematics. That's it. Okay. So if I have 3 RPS parallel manipulator, okay, then it would have a base triangle. You might have seen it has 3 legs and a moving top triangle. So it is RP and S. You have, so if I draw it, it has 3, let's say these are the connections. It has revolute joint over here, a prismatic joint here, and a spherical joint here. Right. So LIs are the so we have For revolving joint we have theta, for prismatic joint we have L, and then we have base radius for this, and then we have side of moving triangle. So for each base we write position of all the spherical joints for for all the legs, and then we also find distance between the joints fixed. There are three equations, three unknown. We eliminate, after elimination we obtain 8-degree polynomial, etc. So I'm not going into details of this, but I hope you have already seen the lecture and have understood this properly, because we have questions to take, and I won't go into much detail. I would move directly to direct kinematics. Okay, so what is the definition of direct kinematics? We saw it for serial robots, right? Can anyone tell me what is direct kinematics? I mean, you just tell me what is given to you and what you want to find. That's it. I'm asking it for serial. What do you know in case of serial? No one? It's very basic question. Come on. What goes in direct kinematics? What are you given and what do you want to find? So it's just the opposite in case of inverse kinematics, but what happens in direct kinematics? Okay, since no one is answering, I'll give the answer. But it is not good. Like, you should tell if you know. It's important. Else, I don't have the feedback. Okay, so in case of serial robots, you are given with joint variables. And what you want to find out? You want to find out end effector, position, and orientation. Okay. For inverse kinematics it is just the opposite. Okay, but things are not same in case of parallel robots. In case of parallel robots, you are given the geometry of the robot and you are given the actuated joints, which joints are actuated. Okay, and then you, what you try to find out, you try to find out what are passive joints and what is the output pose of the concerned link. Okay, so the steps involved here are, you first write the constraint equations, eliminate the variables, it is explained in lecture, well explained in lecture in fact. I'm not going into much detail. Reduce to univariate polynomial, then you solve for it and then you back substitute. Okay, so direct, this is in general statement. direct kinematics of parallel manipulators is much harder than serial manipulators. Okay. Okay, after this, let's move to mobility. So what is mobility? It is range of actuated variables for which real passive solutions exist. Okay. So what is it for 4 bar? We already saw 4 bar, right? And what do we have there? We have condition p square plus q square minus r square should be greater than equal to 0. And it leads to L plus S to be less than P plus Q. That is Grashof criterion. I hope you have already gone through it. Where? What are L, S, P and Q? L is the longest link. S is the shortest link. And P and Q are intermediate. Okay. So all in all, I'll cover just this much part for the revision. But what do we get from here? We understand that parallel manipulators have closed loops. They require loop closure equations, right? They have passive variables and their direct kinematics is difficult. Also, multiple assembly modes are possible and mobility is important. Okay. We learned this, I think. Mm, okay, let's proceed with the question now. Okay. So, just a minute. So, we want to know the first question here is what is the degree of freedom of 3UPU manipulator? Means it has 3 links, right? If you, I hope you understand that. So it is of the same type. It has 3 links, and then here you have a prismatic joint, and here you have U and U. U prismatic, U prismatic. What does this U mean? If you have seen the lecture, you would know what this U means. Can someone tell me? What joint it is? So if it were S, we said spherical, right? If it were P, we said prismatic. If it was R, we said revolute. What is U? Can anyone, have you guys gone through the lecture for the last week? I just need an honest answer. Have you gone or haven't you gone? Because this course would be very difficult if you don't go through it. You can type in the chat box if you've gone or if you've not gone, whatever is your answer. Please tell me. No one is answering. If you have not gone, tell me that you have not gone. That is okay. Now, at this point, I'm not even sure if anyone is listening to me. Am I audible?
Yes,
Okay. So, someone please tell me if you've gone through the lecture or not gone through the lecture. I assume, yes, please.
I have done half.
Okay, okay, that's fine. Okay, fine. So, I would request each and every one, please watch the complete lecture before you come. That would be really helpful for you because that helps you in asking the right questions and understanding a lot of things because I cannot go through everything in detail, right? So, that's nice. Uh, okay. Oh, I had some answers in the chat box. I'm sorry I did not read the chat box. It somehow did not pop up on my screen. Okay. Yes, Shravan Kumar. Okay, I saw your answer right now. Yeah, it's not universal, it's hook joint. Okay, and you have also written N4, J4, Fi1, lambda 3. Okay, very good. Okay, so these are the three identical legs, okay, connecting fixed base and moving platform. So if we count the uh, number of links present, let's check it. So the number of links that we have for the fixed base and then this uh, okay, let's count properly. Fixed base and then moving platform. Okay, so for this is a fixed base and the relative motion between this links is not possible, so we'll count it to be 1. This moving platform will count to be 1, right? And then there are 3 prismatic sliders, right? And then there are three intermediate leg lengths. Okay, so we have three prismatic sliders, which is one per leg, and then we have we have three intermediate leg lengths. So our total n is equal to 8. And if we count joints, which is j, so each leg has one universal joint at base. Oh, sorry, universal, I wrote it. Hook joint at base, which is 2 degrees of freedom. Okay, and then one prismatic joint, which is 1 degree of freedom, and one hook joint at top, which is 2 degrees of freedom. So per leg we have 3 joints. Okay, and for 3 legs it is in total 9 joints. So our j is equal to 9. Okay, now let's work for sigma fi. So sum of joint degrees of freedom we want to find out. So per leg it is 2 plus 1 plus 2, right? We saw here it is 2 plus 1 plus 2. It's 1, not 2. Okay. Which is equal to 5. So for 3 legs, what will have? Sigma Fi is equal to 3 into 5 is equal to 15. Now after this we can apply Grubler-Kutschbach formula for spatial. This is a spatial robot, right? And this is not a planar robot. So degree of freedom is equal to lambda, which is 6, and minus j minus 1 plus sigma fi. Okay, so it is 6 into 8 minus 9 minus 1 plus 15, which is 6 into minus 2 plus 15, which is minus 12 plus 15, which is 3. So the degree of freedom of this robot is 3. So a 3 UPU manipulator typically provides pure translation of the top platform but no rotation. Okay, if the geometry is symmetrical. So if it is not symmetrical, it would provide rotation. So a 3 UPU manipulator typically provides pure translation of the top platform and no rotation in ideal symmetric geometry. So it behaves like a 3-DOF translational parallel manipulator. Okay. Okay. Let's move to the next question. Hope this is clear. The number of loop closure constraint equation used to solve the direct kinematics problem is how much? Is it option A equal to the degrees of freedom of the parallel manipulator? B equal to the total number of joints in the parallel manipulator? C equal to the total number of actuated joints in parallel manipulator? Number D less than, just a second. Okay, less than the total number of passive joints in parallel manipulator. Okay, so any idea how we should approach it? It's conceptual basically, and okay, so you say that universal joint was same as hook joint. Okay, that's fine. As long as the degree of freedom remains the same, it is okay. I learned it as hook joint, so my bad. I was not aware that hook joint is same as universal joint. If it is, then it is fine. Else, it's hook joint. Try to stay consistent with the nomenclatures used in the lecture, because that would be useful for you in the long run and from exam point of view also. But if it is also called universal, it is good. Okay. Um, okay. So let's do this question. So our configuration vector is q, which is theta comma phi, where we learned already that theta is actuated joints and phi is passive joints. Okay, so let n is number of actuated joints, which is our degrees of freedom. We already saw that, right? And m is number of passive joints. Okay, so to solve this, so the question was the number of loop closure constraint equations used to solve the direct kinematics problem is what? So to solve direct kinematics, actuated joints theta are known, but the passive joints phi must be solved, right? So we derive loop closure constraint equation. So although there are m passive, oh, my battery is running low. Just let me plug it in. Hold on for 1 minute. So what I was saying, yeah. There are M passive joints which we do not necessarily, but we do not necessarily need M constraint equation. Why? Because some passive joints may not appear independently. Some constraints also may be redundant. So we break the mechanism cleverly to reduce equations, right? So I'll write it down, whatever I said. But so what happens to solve direct kinematics? Actuated joints theta are known, right? We already know about this. But passive joints need to be solved because they are not being actuated, so we do not do what are the joint variables for them. So passive joints phi must be solved. Okay. So we for this what do? We derive loop closure constraint equations. Okay. But although there are M passive joints, which we already saw, N and M, right? M passive joints, we do not necessarily need all these M constraint equations. Okay. Why? Because some passive joints may not appear independently. They might have dependencies. Some constraints may be redundant. And then we break the mechanism or the loop closure cleverly to reduce equations. Okay, so the goal here is, this is very important, break such that the number of passive variables is least and minimum number of constraint equations are used. Okay, so loop closure equations are only written for independent loops and not for every passive joint. So the number of independent constraint equations are less than total number of passive joints. Okay, So for example, if we talk about, let's talk about 4 bar, because that we have been doing for a long time now. Okay. Total joints is how many? 4. Degrees of freedom we have seen as 1. So the passive joints are 3. Right. But in optimized derivation, we only reduce it to one, only one independent constraint equation. And when would that arrive? When we try to break the link here. Okay. Or let's say here, and then we apply the constraint at this point. So it only one independent constraint equation is there, and that is same as Friedenstein equation that we already saw. So 1 is less than 3. So number of constraints are less than the number of passive joints. Okay. For example, we'll see Stewart platform. You might have already seen in the lecture as well, and we'll have that being covered in the next class as an application for the first octet sensors. But there are 30 passive variables, but we do not write 30 independent loop equations. We choose minimal independent loops. So the number of loop closure equations used to solve direct kinematics is less than the total number of passive joints. Okay, so your correct answer is D. Okay, why? Because only independent constraints are needed, redundant constraints are avoided, because only independent constraints are needed, redundant constraints are avoided, proper loop breaking minimizes equations. Okay, sorry. All right, so that is why it is less. Okay. The set of constraint equations required to solve the direct kinematics problem in parallel manipulators are unique, are obtained by considering all the loops present in the parallel manipulator, must be equal to the number of passive joints used in the problem formulation, must be equal to the number of actuated joints in the parallel manipulators. Okay. So how many constraint equations are required to solve the direct kinematics problems in parallel manipulators? So let's check it. So we already saw that we write the configuration as q, theta and phi, where theta is actuated joint and phi is passive joint, right? So in direct kinematics, theta is given. We are talking about direct kinematics. Theta is given. We must solve for phi. Okay. So we need exactly. So what is the total number of this equation? It is m. We need exactly m independent equations. Okay. To solve for m unknown passive variables. Okay. So this is very important. We do not necessarily use all passive joints in formulation, right? Because they can be independent, they can be dependent, and then all the constraints may not be independent. So because of all those reasons, so we may break the mechanism cleverly. We can reduce the number of passive variables. So at the time of problem formulation itself, we decide how we are going to solve it. Express some of them in some passive variables in terms of others, and we also choose minimal coordinates, right? So if in our formulation we keep m passive variables, then we must have m independent constraint equations, right? If we have fewer equations, then what would happen? We'll get infinite solution. And if we have more equations, then what would happen? It would be over constrained, or we can also call it redundant solutions. Okay. So the other options is, so according to this, what is the correct answer? This is C. So the first option was it is unique. No, this is not true, because different loop breaking strategies give different equation sets, right? So problem formulation word is very important. Okay. And then the other option is they are obtained by considering all the loops present in parallel manipulators. Not necessarily only independent loops are needed. So for this we need to say independent loops are needed. This is different loop breaking gives different equation sets, and the last option is must be equal to the number of actuated joints. This is incorrect, right? We solve for passive joints. Actuated joints are already known in direct kinematics. We solve for passive joints, right? So again, I would like to reiterate what we had seen. break such that Break such that the number of passive variables is least and minimum number of constraint equations are used. So all in all, what do we understand? We understand that number of constraint equations are the number of passive variables used. Okay. So the final understanding here is that direct kinematics means solve for passive joints, and the number of independent constraint equations is equal to the number of passive unknowns in formulation. All right. Okay, I hope this is clear. Let's move to the next question. For the RPS parallel manipulator that was discussed in the lecture, the direct kinematics problem can be solved in closed form. Involve elimination of two joint variables. This is directly from the lecture after derivation. And obtaining a single equation in one joint variable, okay, results in at most 8 possible configurations, and the last option is can always give a real solution. Okay, so let's start this. So what are the unknowns in RPS direct kinematics? So what are the actuated variables and what are the passive variables? So in RPS you might know that prismatic joint is actuated, right? So the actuated variables are L1, L2 and L3, and the passive variables are the angles, okay, the revolute angles theta 1, theta 2 and theta 3, right? So M is equal to 3 passive variables. I'll write it. Let's start this. What are the actuated variables? There L1, L2 and L3 for all the three lengths because prismatic is actuated. And what are the passive variables? Just theta 1, theta 2 and theta 3, right? So M is 3 passive variables, right? Sorry. So for loop closure equations, we have constraint from S pair, right? 3 non-linear equations in 3 unknowns. So these are 3 non-linear equations in 3 unknowns, and then we use elimination process as it is done in the literature. And what does it do? What is the process here? Eliminate theta 1 from, okay, these two equations and then obtain a new equation involving theta 2 and theta 3. From then we eliminate theta 2. All of these steps are written very well in literature, I mean lecture. And then we just obtain a single equation in theta 3. This is the whole process. So yes, two passive variables are eliminated, and after elimination we get 8th degree polynomial. Specifically, that polynomial is in tan theta 3 by 2, right? Tangent half angle substitution we use there, and we get tan theta 3 by 2 ka square. So an 8th degree polynomial, what does it mean? That there are at most 8 possible configurations, right? So the correct options are B and C. The first option is it can be solved in a closed form. So an 8th degree polynomial has no general algebraic closed form solution, right? So it must be solved numerically. Okay? The fourth option is it can always give a real solution. No. Real solutions exist only if geometry allows assembly and actuator lengths satisfy mobility constraints, right? So sometimes no real configuration exists. So this is also not correct. So a very important insight here is that this is a classic property of many parallel manipulators. Multiple assembly modes exist, okay? So for same actuator lengths, there may be multiple possible platform poses. All right, so the correct options are B and C. Okay. I think we'll take 2 to 3 more questions and then we'll done. We'll be done. Okay. Okay. I have an assertion reason question. My assertion is the inverse kinematics problem of a parallel manipulator is easier to solve than the direct kinematics problem. Is it true? I think, okay. Okay. The reason is we don't have to solve for the passive joint variables in case of inverse kinematics. So the options are both A and R are true. A is true and R is false. R is true, A is false, and the last option is A and both A and R are false. Okay. So the assertion is the inverse kinematics problem of a parallel manipulator is easy to solve than the direct kinematics problem. So from the lecture what we have learned that in direct kinematics we eliminate passive variables and get high degree polynomial. For example, 8th degree, 16th degree, etc. Right? But in inverse kinematics we treat each leg separately. So in parallel manipulators, unlike serial manipulators, inverse kinematics is generally simpler than direct kinematics. Just to reiterate what I've said right now, If it is direct kinematics, we can eliminate passive variables, okay, and then we get high degree polynomial, which is 8th, 16th degree, etc. In inverse kinematics, we treat each leg separately, right? So in parallel manipulators, IK is much easier than direct kinematics, and IK is usually closed form, okay? It is leg by leg solution, and it is no high degree polynomial. Okay, so it is true for sure. The first part is assertion is true for sure. Let's talk about the reason. The reason says we do not have to solve for the passive joint variables in case of inverse kinematics. I think you understand that it is false. Why? Because in inverse kinematics, what happens? In inverse kinematics, and effector pose is given. So if it is given, we must find both actuated variables and passive variables. We have to find both. So passive joints in this case must still satisfy loop geometry. Okay. So they are often obtained geometrically from the known pose, right? So we do solve for passive variables, just not via elimination of coupled linear equations like in direct kinematics. Okay, we do not do elimination of coupled nonlinear equations, but then we solve for these passive variables. So the correct answer is A is true, but the reason is false. Why direct kinematics is harder? Because we are given what we are given in direct kinematics, we are given the thetas, only the actuated ones and not the passive ones. This is very important. We are supposed to find phi, which is passive, and these are coupled non-linear constraints. So what does it require? It requires elimination, or it can be polynomial reduction, or it can be some numerical solution. It is not straightforward. Whereas in inverse kinematics, you are given platform pose, right? And each leg length can often be computed independently using geometry, right? So if I want to compute just Li, it would be very simple because it would just be platform point for that link minus base point. So no global nonlinear elimination is needed. Okay, so that is why assertion is true, inverse kinematics is easier, but reason is false because passive variables still exist and they must be determined. So A is true and R is false. All right, I hope there is no confusion. Okay, let's move to the next question. This was what question? 5, I think. Yes. A parallel manipulator cannot be assembled if the values of active joint variables are real. The values of active joint variables are 0. The values of passive joint variables are imaginary, and the values of passive joint variable are 0. Okay, so what is the correct answer? Let's see that. So when can we assemble the parallel manipulator? When is that possible? A parallel manipulator can be assembled. Let's write it. Can be assembled. Hold on. Only if, very important, all passive joint variables have real solution. Right? Why? Why? Because actuated joints are physically imposed, right? So you cannot make any changes to them. You have to bind by the rules. So actuated joints are physically imposed, and passive joints must adjust themselves to satisfy loop closure constraints, and if passive joints require imaginary values, geometry is impossible, right? At the end of the day, it has to comply with the geometry. So passive joints have to adjust themselves to satisfy loop closure constraints. Apart from that, if they have imaginary values, it is not possible to fit into the geometry. So if we take the example again of 4-bar mechanism, from loop closure equation, we got p square plus q square minus r square should be greater than or equal to 0. If it does not satisfy and we get less than or equal to 0, then in this case we'll get phi 1 to be imaginary. Okay, and phi 1 imaginary is not possible. Mechanism cannot close the loop and hence it cannot be assembled. Okay, so the other options that we have, so what is the correct answer according to this? The values of passive joint variables are imaginary. Let's see why the other options are not correct here. The first option is the values of active joint variables are real. Active joints are always real. They are physically set, so they cannot be imaginary. Okay, so there is no issue with this. The second option is active. The values of active joint variables are zeros. Zero is just a special real value. It is nothing it is not imaginary yet. So mechanism may or may not assemble. Like you cannot say. And the other option is the value of passive joints are 0. 0 is a valid real value and nothing wrong physically, right? So, assembly requires assembly requires existence of real passive joint solutions. If passive joint solutions are imaginary, assembly is impossible. So we have a very important insight here is mobility of parallel manipulator is basically defined as what it is defined as we already saw. It is the range of active variables for which passive variables remain real, right? So imaginary passive values means it is outside mobility region. Okay, imaginary passive values means outside mobility region. Okay, I hope that is clear. Okay, I think we have one last question now. The last question was 6. We'll go for the 7th question. Okay, so for a 4-bar mechanism, let the link lengths be L0 is equal to 8, L1 is equal to 3, L2 is equal to 8, and L3 is equal to 4. I hope you understand this is L0, L1, L2, and this is L3. Okay, this is it. For the following two cases, the first case is A is 4.5, okay, and B is 3.5. Second case is A is 6 and B is 2, where L2 is equal to A plus B. So we are having somewhere you break the loop closure, and here you get A, this is B. Okay, so L2 is equal to A plus B, and this is called coupler. We already saw that this link is called coupler. So the coupler curves obtained will intersect at how many points? Okay, a simple question. Let's see the answer. So we are given that it is a 4-bar link, and L0, L1, L2, L3, all the values are given, and the coupler length is A plus B, which is L2. So for the two cases, we see that A plus B is equal to 8, and it is also equal to 8, and our L2 is also equal to 8. Okay, so the only division point along the coupler changes. Only this point would change either in first case or second case. Where we are dividing it, that only changes. Okay, so for a 4-bar, the coupler curve you might have seen in the lecture, it was well plotted there, not plotted, but it was very evident there, or I guess it was plotted. I don't remember exactly, but if you guys remember you can tell me. So yeah, so the coupler curve is 6-degree algebraic curve, and for each input angle theta 1, there are generally two assembly modes. One is open configuration and one is crossed configuration, right? So there are two coupler curves, one for each assembly mode. So what changes when A and B change? The point on the coupler link changes. So same mechanism is there, same assembly modes are there, just different tracing points are there. So each case gives two curves. So total curves considered 4 curves here, but we are comparing just two cases. So each case gives two coupler curves, total 4 curves. Now we compare case 1 coupler curve, case 2 coupler curve. Each case produces two branches. So there is algebraic geometry result that two 6 degrees curve can intersect at most 6 into 6, 36 points. But due to symmetry and mechanism constraints, only finite real intersections occur, right? So for this specific symmetric 4-bar geometry, the curves intersect at 4 real points and not more than that. So the two coupler points lie on the same link, right? They are lying on the same link. The curves coincide only when the coupler orientation is such that both internal divisions produce the same Cartesian location. And this can happen at 4 distinct configuration. Okay? So the final answer here is 4. I think there were no options for this.
Ma'am, here is a question.
Yeah.
Curves intersects 36 points.
Yes. But it happens only for the complete system, like two 6-degree curves. So here we just have we are talking about two coupler curves. So we are talking about 4 real points.
And Gresham mechanism applied when short length plus long length less than equal to intermediate length P plus Q.
Right. I think I have explained that somewhere. Just hold on.
So in that case, we can say where Gresham mechanism is applied,
Mm-hmm.
coupler curves intersect 36 points.
What is your question? I'm not getting your question. Like, so this is the Grasov criterion, right? Uh, so L plus S is less than P plus Q, where L is the longest link, S is the shortest link, and P and Q are intermediate. So what?
This is a Gresham mechanism. In that case, coupler curves intersect 36 points.
Mm-hmm.
In all cases, it may define.
So that was a general statement. If you have all the 6-degree polynomial curves, then if, for example, in our case, we are just looking at two criterions, so we have two coupler curves. But then in general, it is going to be 36 points.
It depends only coupler curves, number of coupler curves.
Mm-hmm. So let me take this through that route. Just wait. Where is it? Okay. So, uh, okay. So this would be completely through Grashof criterion and geometry and no algebra. So let's say in our case L naught is 8, right? And L1 is 3. L naught is 8, L1 is 3, L2 is 8, and L3 is 4, right? So the shortest S is 3. Longest L is 8. And what are the others? Intermediate ones, they are 8 and 4. Right. So from Grashof's condition, let's check it. 8 plus 8 plus 3 is less than 8 plus 4. Right. That means 11 is less than 12. So this was satisfied. It is true. So this is a Grashof mechanism. Okay. So at least one link can rotate fully. So here the shortest link L1 is equal to 3 is adjacent to ground. So for that, the theta 1 can lie somewhere in between 0 and 2 pi. So for this graph of 4 bar, for most input angles, there are two assembly configurations, either open configuration, cross configuration. That is true. So for each input angle, there are two coupler curves. Okay. Now we are changing the division of the coupler. Okay. So a plus b is 8 is equal to L2 is equal to is a constant. So for the same mechanism, we have the same crank motion, same two assembly nodes, only the tracing point is changing here, as we mentioned last time also. So since there are two assembly modes, we have two curves and two cases, means four curves total. So intersection happens when we have a division point at A and A dash, and if they coincide in space, that means the coupler must align such that both internal division points lie at the same location, and it can happen only at special configuration. So crank can rotate fully and the coupler rotates continuously. It crosses certain symmetric position. So there are two toggle positions and there are two assembly modes. Each toggle gives two intersections. So we have two toggles into two modes is equal to 4, and hence we have 4 intersection points for this for just these two configuration when they are given to us. Okay, and the number 36 comes from a general result in algebraic geometry called Bejout's theorem, right? So the coupler curve is a 6-degree algebraic curve, right? So it comes from eliminating joint variables in loop closure equation. I hope you have seen the derivation. And the degree of the polynomial that we get there is 6. So how do we obtain the number of intersection points? So it comes from M and N. Right. So M into N gives me maximum number of intersection points. So each coupler curve has degree 6 and maximum intersections that can happen is 6 into 6 is equal to 36. That is where 36 comes from. So these 36 includes intersection points, includes multiplicities, they may be repeated, and includes points at infinity, is a theoretical upper bound. It does not mean that we will see 36 real intersection points physically. It is not necessary. Okay, and for this problem we got only 4 because mechanism geometry restricts real solution. Most of the 36 intersections are complex, many are repeated or are at infinity, only a few are real and physically meaningful. So 36 is a theoretical maximum, not the actual real count. Okay, so in our case, we have maximum intersections as 2 into 2, which is 4. But they might also not be there if it goes to 0, infinity, or some imaginary number. So 36 is just same idea, but with more number of coupler curves. And due to degree 6, we are considering it. Okay. I hope it is clear. We are done with today's lecture. If you guys have any question, you can ask me. And uh, next time we are going to have applications of parallel robots where we are going to see sun tracking using 3-DOF manipulator. Right. And Stewart Go platform based force torque sensor, as I already said, and vibration isolation using a Stewart Go platform. Okay, once we are done with this, we'll move to velocity and static analysis of manipulators. Okay, we'll see what is Jacobian for serial and parallel manipulators both. We'll address singularities in these manipulators, and we'll also see the statics of serial and parallel manipulators. Then we'll later go to redundancy and dynamics, etc., and the nonlinear control and all. Okay, so by the way, how many of you know this? I have read control system course. Like, are you familiar with control system? It is very important because when we move to the module, this non-linear control of robots, of the manipulators, then there you will need to understand at least classical control in order to learn non-linear control. So I would suggest that you should go through control systems lecture. Okay. And it is very simple. You just need, don't go through everything in control. It is not required. You don't need to know root locus, etc., compensator, etc. But just try to know how control systems, like how do we control a system, and then what are the variables that we deal with, what do we try to control, and then you might also know when do we say the system is stable and when the system is unstable. So these are the things you should know. Okay, so please learn control system course. If you want me to share a reference, I can share. But if you are familiar with the lecture, it is widely available on YouTube. The Control Systems Engineering by Professor Shankar Ram from IIT Madras. You can go and refer to that lecture. It is a good lecture and you'll get basics of it. You need not watch the whole lecture, but a beginning of it, so that you are able to understand control. Because here you are going to deal directly with nonlinear control. It is better that you learn somewhat classical control before diving deep into this. All right. So that is what I felt that you should know about it. And if there is something to share, you can share, else we can close the session. Is there something that you want to talk about?
Okay, thank you, ma'am.
Okay. Okay. So thank you, class. We will meet on Monday at the same time, 6 to 8 p.m. Thank you. Bye.